Assalamu alaikum. My name is Osama, and in this presentation, I will be discussing our course's final project, DC motor control using an H-bridge. The following people are my group members, and together we worked on designing, testing, and implementing H-bridge circuits. So, a brief overview of our H-bridge circuit. The object of this project is to design and implement either a BJT or JFET controlled H-bridge, capable of bidirectional control over a DC motor that is integrated into the configured circuitry. That means that the motor can either be turned clockwise or anti-clockwise, depending on the input provided by way of single-way push buttons. The circuit, in principle, operates like an exclusive OR gate, uh, where if one input is provided out of two, then the circuit will operate according to the specific input um, provided. Whereas if both inputs are missing or both are provided, then the circuit will not function. This is because when zero inputs are applied, meaning the buttons aren't allowing current to pass through, then there is no voltage available to be, or there's no current available to be supplied to the DC motor acting as our load. Um, Whereas if both buttons allow current, then the currents go to the same center where the motor lies and cancel each other out because they are of equal magnitude, but they are traversing in opposite directions. In addition to these parameters provided, the DC motor is also required to operate at a voltage of 9 and must also draw a maximum current of 2 amps. And lastly, within our circuit, we must implement the uses of an optoisolator or optocoupler, specifically the PC817 model. This is, of course, mandatory for the specific circuit as our parameters were set by our instructors and thus should be implemented. Here is a list of the materials we used for our circuit, starting with our four high power NPNs, TIPs, or TIP31, followed by our two PNPs, TIP32, also high power transistors. Following that, we have two terminal T blocks, one for the DC motor, where the DC motor will be attached, and the other for our battery to supply voltage to the entire configuration. Um, in our case, that would be a 12-volt battery. We also used a fiber PCB board to implement our circuit, and as discussed before, and sorry, and as discussed before, um, yeah, we also used a fiber PCB board to implement our circuit, and there are also two push buttons attached to the configuration. One to rotate the motor in the clockwise direction and the other in the anti-clockwise direction. Additionally, we had resistors in place to regulate the current throughout the circuit to protect and meet the parameters of each individual component present in the circuit configuration. Um, we also used two opto-isolators operating in cohesion with push buttons to activate a singular path for the motor to turn in one direction. Opto-isolators are primarily used with AC sources to protect the circuit from voltage rises, but in this specific circuit, it basically was responsible for activating the transistors, which then created a path for the motor. And the working principle of the octocouplers or opto-isolators will be elaborated on further ahead in the presentation. Lastly, we have the DC motor itself and the flyback diodes, R1N4001. The purpose of the flyback diodes is to protect the transistors because when the circuit is suddenly turned off, heat is stored within the transistors and is dissipated, which heats up the internal circuitry of the component, and over time that would affect the general or overall performance of the transistor, eventually leading to it not functioning at all. Hence, we have them placed parallel to the transistors so that it can also contribute to the heat dissipation instead of the transistors being on their own. So, coming to H bridges, the configuration itself. So, what is an H bridge? An H bridge is a specific type of formation of transistors, in our case of BJTs, that enable the circuit in various ways to implement relevant input characteristics and control the direction of rotation of a motor acting as the load for the circuit. As previously mentioned, the push buttons serve a core function for the circuit as they enable each side of the H bridge and determine the overall functioning of the load. Implementing the opto-isolator was challenging at first because, or within this type of configuration, but once its logic became clear and its working principle was explored with our testing and troubleshooting, it was also understood that since the opto-isolators are supposed to activate the H bridge, so the transistors in place, then it must hold true that the push buttons should therefore activate opto-isolators by allowing current to flow to the anode of the LED or light emitting diode within the isolator, which then turns on the phototransistor when it detects that light. If the opto-isolator is not activated due to the path being blocked by the push button when it is in off state, and so in consequence the LED is off, then the circuit should not operate at all. Next we have, or moving on to the workings of every component. We have the DC motor that we used as our load for the circuit we designed. A stage in our construction of the circuit was when our initial design compensated for a motor with a high coil resistance, meaning that it required a significantly low current to activate optimally. This means that low current passed through the load, which also meant low current passed through the transistor terminals or the TIP transistors in place. The motor itself had a nominal voltage of 6, relatively high torque, and a high RPM along with it, which was approximately 9,000. So it was pretty easy to activate the motor at first. In the initial design, only a current of 36.6 milliamps passed through the load as shown in the schematics ahead, which we will get to, and it was enough to activate the motor and reach a high voltage across it, uh, specifically 10 volts or slightly above. But according to the parameters we discussed earlier, though we met the requirements for voltage across the load, our DC motor, it was also required in cohesion that we achieve a high current value for the load as well. Given that the maximum allowed was 2 amps, it was then further elaborated by our lab instructor that a minimum of 1 amp must be achieved for our circuit designs. So, with a few adjustments in resistance throughout the circuit configuration, mainly lowering it in different places so that the current values increase, we were able to meet that requirement. We also brought in a new motor, a 9-volt geared DC motor that also operated with a high RPM but had significantly lower coil resistance. 3.5, I believe, 3.5 ohms to be precise, compared to the other motor, which had around 200 ohms. This heavy duty motor, at the very least, required 1 amp of current, which coincides with the parameters we were given, and so the following procedures were carried out and implemented effectively. All of this was also made possible by the TIPs we used, which are quite dynamic in their operations because they can work on very low current, as they did with the high coil motor, and they can also handle large currents as they did for the low coil motor. So there's no need for a change in model, um, or that it wasn't required with regards to the transistors, since it was a dynamic um, functioning transistor capable of operating in both conditions. Moving on to rectifiers. Now, rectifiers are responsible for converting AC current to DC within a circuit configuration, and is especially useful when using components that are sensitive to or do not operate when an AC source is applied. This process of conversion is better known as rectification. With all of this in mind, it is evident that within the circuit, this process is not needed, nor was it asked to be implemented because there is no AC source present in the entire configuration. Um, for the most part, we're only using a battery which provides a DC voltage to the configuration, so a rectifier would serve no real purpose in this circuit. As for voltage regulation, such a function is described as a measure of stability of a transformer's secondary output supply when it receives a constant primary voltage. This is measured in percentage, and the lower the percentages, the less deviations there are, hence the more stable the output of the transformer is, and in consequence acts in coherence with the rest of the components within the configuration. Voltage regulation is also related to the function of ICs, or integrated circuits, which are or regulate voltage supplied to them, long as it is a DC voltage or a rectified AC voltage, and they can either provide a fixed voltage, um, like an LM7805, which provides a fixed 5 voltage at its output, or it can provide adjustable voltages like an LM317, which we used in our previous project with the step-down transformer. And this, of course, adjustable voltage is made possible with the placement of resistors um, about each terminal, which then determines how much the regulator provides at its output. And all of this is ensured, or its functioning is ensured by way of maintaining the voltage supplied to the regulator so that it is confined within the limits of the regulator. Otherwise, if it exceeds it, then the functionality of the component will deteriorate over time and eventually reach a point where it does not function. So here is a schematic of our low coil motor design, and I will briefly go over the functioning of the circuit. So basically its working principle. Starting with the 12-volt battery up at the top, it is supplying a constant voltage, but the transistors at the receiving end, Q5 and Q6, do not receive it because they are in the off state. And why are they not on? Because they have no base current. And the only way they can have base current is if either Q1 or Q2 is activated. And the way that these two transistors are activated is if the opto isolators are also activated, providing the transistor a sufficient value of base current through its emitter. So to have those on, push buttons must be in the on state. A current then passes through, supplied from the battery, and enters the LED or light emitting diode um, within the isolator through its anode and out its cathode into the ground terminal. This turns on the LED, and its light is then detected by the phototransistor present beside the LED. Once the light is detected by the phototransistor, it then turns on and allows current to flow from its collector to its emitter. Now, suppose we turn on the push button on the left hand side. So the opto isolator U1 is turned on, which then emits current into Q1, which is an NPN. Since Q1 is now activated, it can collect current and emit current into Q4, which then activates as well because it now has received a base current. Q1's collector is attached to the base of Q6, which is a PNP. And a PNP, as we know, receives current from its emitter and emits current from its collector and base. So with Q1 activated, meaning its collector um, can receive current, that means that Q6, the PNP, can now emit base current into Q1's collector, meaning Q6 also turns on, um, and with Q6 and Q4 turned on, we now have a path for current provided by the battery and sent to the motor through and into the ground terminal. On both sides, the circuit operation is identical, meaning that if you turn on the right side, then it will mirror what we just explored and elaborated on the left side. That means U2 will turn on, emitting current into the base of Q2, which then turns on, and Q2 then consequently also turns on Q5 and Q3, creating an alternate path through the motor and turning it clockwise. As we explained earlier, we also used flyback diodes and placed them parallel to the TIP transistors, or the ones that are receiving current directly from the battery. So that would be Q5, Q4, Q3, and Q6. And these are in place to protect those components from overheating, providing a path for the current to flow. And when the circuit turns off, and heat dissipation is not solely resting or is not, um, assigned solely to the transistors, because now with the diodes in place, they can also help with power dissipation. Moving on to the schematics, we have the design with the low coil motor. In this circuit, each component is organized and placed as explained previously, and as we discussed earlier, with this specific motor and the design configured to compensate for its parameters, we have a high current of 1.6 amps received by the PNPs in place, followed by a collector current of 1.55 amps, which the motor receives. This current is perceived by the collector of the NPN below, and the motor or load achieves a voltage consumption of 8.74 volts. The base current range rate excuse me, ranges anywhere from 88 milliamps for the TIPs, as they can handle high currents at their base, and can go down to 2.4 milliamps, which portrays how dynamic these transistors really are. So for our high coil motor design, the values of the components are significantly higher. The resistors are achieving a low current, which then is supplied to the motor, which then achieves a voltage of over 10, or specifically 10.4 volts, despite the low current, and that is because its coil resistance reaches a value of over 200 ohms. the rest of the components remain in place all the same. The working principle remains the same. There is a slight difference, and that is the addition of the two resistors attached to the emitter of both PNPs above the motor. So Q5 and Q6 now have on their emitter side R7 and R8, and that is specifically placed to limit the current um, passed through that transistor, which then passes through the motor. Here is the PCB we designed according to the schematics. Now it's important to note that we used, or I should make it clear that we used the low coil motor because it was communicated to us that we needed to have at least 1 amp passing through the motor, and with the high coil that simply isn't possible because then the voltage would be too high for the motor and it would eventually stop working. So we used the low coil circuit design for DC motor, and this PCB design is for that specific schematic. Ahead of that, we have our 3D design. So this especially came in handy because when we started off, we had our breadboard testing, and when we verified that all the components were working and the configuration was functional, we then moved on to PCBs after the chemical process, after the drilling. This is what helped us place our components accurately, and this also helped us determine whether the components would fit on the given design. Because when we design the PCB, of course, all the components are in place, but when it comes to 3D, there is a amount of space that each component gathers or takes up, and so the 3D design helps us determine if there are any areas where components might clash or that they might take up each other's space, etc. And so this was crucial in that process. And this would be the automatic test bench that we designed. And the working principle remains exactly the same, except that with this now ground is enabled through this button at the bottom and the two at the top, forward and reverse. You can see that they are connected to the supply node up at the top. And so the forward would then activate this right hand side opto isolator, this one right here, and would basically turn on Q3, Q5. The reverse would mirror that function and turn on the left opto isolator, and which would then of course mirror the function turning on, I believe, Q4 and Q. Alright, sorry about that. So this is the automatic circuit that we designed, and here is the code for it. Now, over here we assign integer values to each function. So enable, reverse, and forward each have a unique integer assigned to it so that they function, they operate separately. And there again we have the loop and turning on the LED, and that's related to the function where we had an LED attached to one of the buttons, which then is operated after a specific delay. So the voltage rises to a high value, uh, then there's a delay, and then it goes to a very low value, which means the LED turns off, and then there's a delay, and then it goes back to hot. And this loop, this function is operated within a loop, and that's how those terminals work. So this is our final PCB. We soldered it, we drilled everything, attached those components. Um, we checked continuity across, and we took test points to see if each component was functioning. Um, there seemed to be an overall issue with the soldering. Now, we checked that it runs successfully. The configuration worked perfectly on a breadboard, and that's how we verified that each component was working and that the circuit configuration would work. And it was also tested right before we were supposed to activate. Um, we started our PCB, but evidently there was an issue in the soldering, possibly an issue with dry soldering. We checked continuity multiple times. It wasn't short anywhere, so that seems to be the only plausible um, issue at hand, and we didn't get to resolving it. And that's the end of my presentation. Thank you for listening.